Hey, thanks, Nick. Appreciate it. Hello, welcome to today's webinar. As Nick has said, this is going to be about polymers in the automotive market and what does Instron have that can assist with these materials in this market. So let's start at the materials level testing, and by that I mean what are the tests that are done by the polymer, both by the polymer producer in automotive and also the polymer user or end user. So these are the tests that define the properties of a material. So polymers, as we know, have become a significant material in an automotive market, with the increase being driven in lightweighting and trends and regulations. Polymers have unique properties such as energy absorption and the lightweighting mass that make them suitable for a wide range of applications. And besides the energy absorption and the lightweighting, the unique thing about polymers is the flexibility that they can give to a designer or an engineer in this marketplace that over and above what you can do with metals. So the illustration we have up here shows some of the components that are made from polymer materials. And it's estimated that currently there are approximately 30,000 vehicles, parts in a vehicle, out of which 1/3 are made from polymers. And of those polymers, that there are approximately 39 different mixes or polymers that go into the making of the vehicle. So of those 39, 70% come from the 4 or 5 polymers that you see on the slide now. Not only have we listed what the polymers are, but also listed are the properties or what characteristics about the polymer that make them uh, choices in automotive, as well as where are the common applications for them. So good polymer selection is not just about choosing the strongest material. It's also about choosing the most balanced material in relation to what is it you need it to do and what are you making out of it. So to ensure that both the polymers selected and the products produced are the best for your end application, you need to have the proper test equipment. And the purpose of today's webinar is to highlight what those products within Instron's portfolio to help characterize materials and provide insight into some finished parts. And as we show here, luckily Instron has a full portfolio of polymer testing equipment. So I want to talk first about impact testing in the automotive market, and specifically the use of drop tower systems. So as you might imagine, automotive industry is one of the primary markets that use drop towers. Car manufacturers need to ensure that the components such as bumpers, fascias, engine covers can withstand impact. So they need to ensure that the materials they use can withstand those impacts. And that includes impacts from other vehicles, from road debris, from accidental, kid too close to playing baseball, too close to the driveway. So a drop tower can be a very simple system, just a mass falling from a height, simple basic system. But then you can also add air cylinders or springs to assist the mass, increasing velocity and thereby increasing impact energies. You can integrate a thermostatic chamber into a drop tower, which would then allow you to do testing at both lower and higher temperatures to define material characteristics at different temperatures. And you could even include a large base that would allow you to put a full component and test a full component on the tower. So since everyone in attendance today may not be familiar with the drop tower and how it functions, I thought we'd do a quick review. Essentially, a drop tower consists of a latch that holds a falling mass. To the falling mass, we have a velocity flag attached, as well as a top or load cell, an insert that attaches to that load cell. We have a velocity detector that watches as the flag passes through to give us velocity. We have shock absorbers or a means to stop that mass once it's completed the test, it's impacted the sample. And we have a fixture that holds the sample. The way the test works is we have the latch take the mass to a defined height. It's released from that height. The velocity flag, as it passes through the detector, captures the impact velocity. The top load cell impacts the sample that's on the fixture. And then once that load cell has passed through that specimen and the test is complete, the mass comes into the shock absorbers and it's stopped. Then we have an automatic retrieval system that comes down, retrieves the match, puts it back in the latch, and returns to the drop height. So why do we do impact testing with, say, a drop tower over a pendulum? Pendulums we know are good impact systems, but they provide a single point of resilience or energy absorbed on a notch sample. Um, Using a drop tower lets us do a multi-axial test wherein the sample is allowed to fail during the impact event as, if you will, the material wants to fail. So using a drop tower, I can vary the speed. I can vary the velocity, the height, so I can vary the impact energy and get a feeling for how any one material may react to impacts given at different velocities. So looking for strain rate sensitivity to maybe a material is more sensitive at a higher velocity to an impact event than at a lower velocity. Um, the test also serves several important purposes, such as how well can it withstand penetration? How does it behave when it is impacted? How does it deform or displace when it's hit? And also we can define how much energy is absorbed by the material under an impact event, which translates to how much does that material pull away in an impact event and absorb and thereby protect further down the road. So all this data is key in helping to determine what the correct material for the application is. So one of the best benefits, obviously, is we can define when we add a chamber to it, or even just at room temperature, we can define how tough the material is or how ductile it is. So the tougher the material, the more ductile it is. The more ductile it is, the more energy that material is pulling away from the impact event. So this lets us pick a material that fulfills the role of being an energy absorbing. And the high speed impact test lets us see and find this and helps make engineers make an informed decision about best polymer for energy absorption, but also for perhaps the part, the end use of it, where it is in the car. So another trend we're seeing besides the puncture test is in the market, we're beginning to see a move towards high-speed tensile impacts. Um, we know that tensile impacts are good, or well, tensile testing is good at helping establish the properties, mechanical properties of a material. Um, a stat, just a normal static system, however, can't necessarily provide a higher impact or subject that material to a high speed impact. Uh, Servo hydraulic systems can, of course, do this. There are certain infrastructure and maintenance, concerns with a servo hydraulic system. So a drop tower can serve as a middle ground, if you will, between the traditional static frame and our velocities, our servo hydraulic systems. So another trend we're seeing in conjunction with the high-speed tensile impact is bringing in high-speed cameras to record the impact events. So what we can see is we can, with the high-speed camera in conjunction with the tensile fixtures, we can subject the material to a tensile test at higher speeds, and we can see what the failure is. And when we take the video and sync it with our data acquisition, in our case, Blue Hill Impact software, we can watch and see a whole picture of at what point, where are we breaking, what load are we seeing, what time is this occurring in, where's elongation starting, what does it look like? That's one of the news trends we're seeing. Another trend we are seeing is the use of DIC. Here again, we can sync this up with our high-speed camera, and we can see with the digital imaging correlation, what are we seeing in the impact event. So with this, I believe, Peter, I turn this over to you.
Great stuff. Thank you, Stephanie. Hopefully, you can all see me now. If not, then that'll all get sorted. Right. So, going on a little bit from what Stephanie was talking about, I think it's a really good point to go straight on from tensile impact. And thank you, Stephanie. You've laid out a few of the things that I'll also apply in what I want to talk about. So that high strain rate performance, and tensile impact is a very approachable way to get some data on that. It's something that, from the dynamic systems side, has been a strand of our business for a long time, really important in automotive. Started in the late 1990s with metals and the NCAP safety business, really understanding what happens in that catastrophic failure of crash modeling. So you need to model well, you need good material selection data. But this is the layer beyond just peripheral components like Stephanie alluded to before. We need really precise data. And you can see this very nice model, which some folks very kindly shared with us, one of our customers. This is the result of, they take their high strain rate data, they build a model, and then they actually modeled the outrigger for a truck, this was. So strain rate sensitivity is particularly noticeable in polymers. So plastics, if you're going to start using those in automotive, you absolutely have to have this data. You look at the little graph I've taken there from some work quite a long while back from University of Dresden, and you can see that the strength of the material can actually double between a normal static test and a high speed test representing the sort of strain rate you get in crash conditions. Now, for a lot of the world, this just doesn't matter. But as I say, we really have to worry about it once we start putting plastics into important parts of the crash structure of a vehicle. And that is where this is going. And it's all very much to do with that drive for lightweight materials, lightweight vehicles. Um, so how are we going to do that? You've seen the approach of making a tensile rig, which sits inside a drop weight machine. Now, I'll sort of summarize the differences between drop weight impact and the servo hydraulic solution kind of at the end of this section. But there is another way, which is a very customized, a very specialized servo hydraulic machine. So at this point, we're going to accumulate a lot of oil at pressure, and then we're going to fire it through, open a valve and fire it into a cylinder in a profiled but very rapid sense. And we're going to get a similar sort of strain rate, a similar velocity to what you see with drop weight. But there are some different things we can do. There's a little bit of anatomy of the system here. We have to, if anyone knows already about servo hydraulic actuators and machines, we have to go to a lightweight, a race licensed actuator, as it were. And we do need to have, because unlike the impact system where you're out of contact, normally with any fatigue or tensile testing system, you're holding on to both ends of the specimen, which we are here, but we somehow need to accelerate up and then grab it at that point. So I'll come to that in a moment on my next slide. The other thing I'm pointing out here is that we have a high-speed camera here, and that's not just to see qualitatively how the specimen fails. It is going to be our primary strain measurement. So really, the expectation in today's world is that you collect good strain data for the full gauge section of your specimen, and when you are up at, let's say, 2, 3, 4, 20 meters per second, these very high strain rates, really, image correlation is the only game in town. Yes, people historically used strain gauges. It still only got you part of the test, and you had to infer the rest. So how are we going to deal with this matter of accelerating up to speed? And this is a little illustration. I'm not going to spend much time here in terms of the lost motion gripping system, where you accelerate up to speed and then you will grab the specimen and then apply the loading. Now, the image on the right-hand side there should be animating, but it doesn't seem to feel like it today. That's absolutely not a problem. You can see the sense of it from the illustrations and the cutaway diagrams there. So this is very much more than just a fast tensile test. And it's a discussion that Stephanie or I would have with people at quite some length on another day about how you deal with that, getting from that quite noisy data, which has extra vibrations that just don't exist. And you have to get rid of those, you have to analyze that. And there's more careful test preparation. But we have systems, we have dedicated equipment, we have dedicated software, and what used to be 10, 15 years ago, only university research work, we can supply a good system that can be used routinely and get really nice reproducible results without it being a PhD project. I said I was going to highlight the sort of compare and contrast between drop weight and high rate servo hydraulic. Now, with drop weight, you're controlling the initial velocity and the energy available at your contact point. After that, it's in the lap of the gods, as they say, or more to the point, the response of the specimen determines what happens after that. Do you punch through and lose very little velocity? Do you damp it? What happens there? It's great about energy absorption. It's great about damage tolerance. Compare this with servo hydraulic. We can exercise some control and we can carry on forcing right the way through our specimen and punch right through with whatever's required and keep the rate of loading pretty stable, keep the velocity pretty stable. And this is really useful for strain rate effects, especially in more ductile materials. Now, maybe that's good, maybe that's bad. for what you need, but it gives you a different set of options. And certainly historically, it gave you some better options for different types of coupons. But hats off to my friends in Class Division. They've been solving a lot of those problems with drop weight for recent years. So I'm going to sort of stop there on the high rate side of things, and then turn to something completely different. Again, very much in the sort of design space more than routine, which is to talk about fatigue. Now, again, not a routine test. It's never really been a routine test in the plastics world, but it's coming into being. It's coming into a real focus within recent years for automotive, especially. And the goal again, lightweighting. It's really more design and development modeling and generating those material cards for FEA. It's often with highly reinforced grades, and there's, what people talk to me about is some of the semi-structural components. A quick insert here. Obviously, not everyone will be very familiar with fatigue. Hopefully, most folks kind of vaguely remember the word from doing something at college. We're talking about the resistance to cyclic loading, to repeated loading. So if I load something and it's like way below the static strength, great. What happens if I do that 100 times? Worse than that, what happens if I do it 1,000,000 times? And we're really fatigued about building up that relationship between how gently do you have to load something for it to survive, well, for a given lifetime. Testing needs within plastics fatigue are pretty straightforward. We're looking for something simple and reliable. We don't need a very high force capacity, but we do need, therefore, nice high control fidelity. It's also because, as Stephanie touched on, you have climatic chambers. It's just as important for fatigue behavior as it is for impact. And there are some standard test methods out there. They've been out there and published for a long while. They are not particularly widely discussed. I do a lot of work with the metals community, and there's a lot more facing this very strict standardization there. So what are we going to do to achieve this? The traditional universal test machine, what often people refer to as an Instron, it's not suitable for this. And we've talked about that in previous webinar and some future ones. The most cyclic work those can do is going to be below about 1 hertz, 1 cycle per second. So you could be talking literally weeks for each specimen. And if you need to do between 6 and 12 or even 18 specimens, this is a non-starter. So what we have is the Electripulse product range. It's been out there for 2 decades now. Started out targeting the biomedical industry. It does all the good stuff that you get out of a servo hydraulic machine, but there's no oil. It's lovely, it's clean, dry, all electric. So that's our approach. You get very high fidelity, as I say, good capability of monitoring. You can also do things like calculate what's happening to the behavior of your plastic as that fatigue is going on. So things like stiffness can actually reduce while the test is going on, while it's still in one piece, but it's not quite as stiff as it used to be. I'm going to finish up with a little comment around this, and I've said that this is becoming more and more of interest. I am going to refer to a project called Campus. It's a Polymers plastics properties database. It's really been geared up by the automotive industry. It's something we've engaged with, particularly around the fatigue side of things. And they have been doing some pre-standardization, because something that happens in fatigue of plastics is that as you're cycling that force, you actually build up heat. To oversimplify a little, it's frictional energy inside the coupon, inside the specimen. Now, it's something that, in fact, was an issue for the structural composites world 10, 15 years ago. We generated our own solution for controlling that by modifying the frequency of the test. That's been on the market since 2013. Rather a surprising time ago, myself and my colleague Dr. Hurl developed that shortly after I joined. Campus are there. Some of those groups use use our technique, our equipment. As a whole, they're looking at a different approach to again using cyclic energy calculation and then controlling the test using that. So that's quite a deep dive, but I would really say that it's just the impact of this project is very far-reaching. There are a lot of major plastics manufacturers out there. There are a lot of major automotive companies. They're all engaged in this, and we have fairly regular meetings. And it will go towards ISO standardization and presumably ASTM eventually as well. So that's what I wanted to say. The two themes of that more sort of advanced materials characterization, very much the high speed and the fatigue. Those are the things which we see a lot in automotive industry. I'm going to hand back to Stephanie, who's going to talk a little bit more about system and component level testing.
Thank you, Peter. I learned a lot from that. So thank you very much. So when I'm looking to finish off, I wanted to talk about something with drop towers that we're seeing a trend in the market is actually impacting and testing parts of vehicles. So we think about bumpers. Uh, we talked about a puncture test on the material itself at the beginning, where you take that material, that polymer, and now you form a bumper. Being able to take that bumper and perform impact tests on the bumper to see how, again, does that polymer pull energy away from the impact event. We have that. Bumpers have to be attached to frames. So another impact test we have some customers doing is actually crushing the structures used to attach bumpers to vehicles. They'll start with just a column, empty column, crush it, see how it reacts, get the energy absorbed from that test, then turn around and use, say, a polymer foam in that structure, run that same impact test, and see that what the energy absorbed value is, which is usually more energy. It holds it off with the filled. Airbag covers, safety, for the occupant, obviously more cars, vehicles. I think just about everybody now comes equipped with an airbag cover. We have them in the steering wheel, in the passenger side. We have customers that perform impact event tests on airbag covers. They will cut the passenger side out, frame, put it in the drop tower in a custom fixture and impact it. And as well, we can take the driver's side airbag, impact it. And part of the whole process with this impact is to be able to see how does it open. It's critical with an airbag that the flap separates in a particular order. So we could take the airbag cover, put it in the drop tower, put a high-speed camera on it, and then watch how and make sure that that opens in the proper sequence. We've seen fuel tanks, gas tanks have moved from metals to polymers. Again, more impact resistant, better material for design. Gas tanks can now be designed, fuel tanks designed to fit various different compartments, maybe than they could have before. Also, we have some customers who are impacting the tanks used to contain compressed natural gas. Uh, and exterior finishes. Let's be honest, vehicles see all sorts of impacts, be it from stones, from road debris, from kids playing too close to the car, or of course, there's always the dreaded uh, encounter with the runaway shopping cart in the parking lot. We can take the drop tower and a configuration similar to the puncture test, but this time we're using a sample of material that is then coated with a polymer. We impact it. We can design or have inserts that attach to the load cell that mimic any number of things, stones, corner of a shopping cart, and perform an impact test on it to see how does that finish hold up to the impact event. And I'd be remiss if I didn't speak just quickly about polymer use inside and what do we worry about there. Obviously, we have concerns with heat and how do these polymers for use in that's the dashboard of the car or some of the other trim, how do they hold up to heat? And there we would use our HDT VICAT systems, VICAT test being to take a polymer and we heat it, put it in the system, it gets heated up, and we begin to watch for when does that soften to the point where we can penetrate a millimeter, or the HDT side where we will then deflect a certain event in bending. Okay, and with that, that concludes my final thing about testing of finished components with our systems. And I will turn this back over to Nick.
All right. So this is the stage where we jump over to some questions from the audience. We received some with the registration, so I'm just gonna start with some of those. Um, so first up, we run the same tests, but still see a lot of variation. Where do you usually start troubleshooting that?
Um, if we're talking with you say a drop tower, I would start looking at so I would start looking at, depending on what I'm testing, if I'm using a clamp, do I have the right pressure? Uh, I pay attention on polymers to, especially a finished part, let's say the gating, the flow. Am I testing parts of the finished component? Let's say, are they cut from the same area, or am I at different locations, say gating areas or curves, things like that? And I would begin to look there for why am I seeing a variation.
Yeah, I
Okay.
think I'd agree. It can be the same in tensile and fatigue. And the more reinforcement you get, the worse it gets. And I was just going to add that if you're looking at something very highly reinforced, and this is a tensile test or a fatigue test of any sort, you might need to start looking at alignment. It's absolutely critical with structural composites to deal with that, because if you're not loading your component dead on line, you're actually not quite measuring what you think you are. So just some other thoughts, not knowing exactly what we're referring to here.
Okay. Next question, how do we determine whether we need an instrumented impact system versus a traditional pass-fail setup?
But with instrumentation, for us, for me, it's I get to see more about what's happening than with an uninstrumented test. If it's an uninstrumented test and I'm visually looking and trying to decide what is failure is it a failure? If you're dealing with a material or a component, say that's multi-layered, multi-structured, it could be that on the outside, I see nothing, but as I impact, the outer surface comes down into the inner layers and there's damage there. I won't see that unless I have instrumentation, unless I have that load cell watching the material fail during the event. So that for me
Yeah,
becomes
you
when I move.
yeah you basically otherwise it's either it's punctured or it's not, right?
Yep.
Okay, what are some of the best practices for conditioning samples prior to impact testing?
For me, use a chamber. I mean, I say that simply because I have my fixturing sitting at the same temperature as my samples. Other ways is you can, if you have, depending on what you're testing, if you have, say, a freezer or your avail can walk-in freezer or a lab freezer, you can precondition the samples there and then move them into the chamber, the test area, with the chamber and test there.
Next question, where do you see the biggest gaps between standards and real-world performance requirements?
Ooh, I mean that's an interesting one. It's gapping. I think there's an aspect that a lot of the standards that we work with within the materials, they're about materials testing. They're about kind of giving a consistent, comparable measurement. Um, and then what you do with that is like I was talking about, you pass on these behavior characteristics to the modeling. So um, I don't know. It's definitely with because you've worked a lot more with the component test side of
Uh-huh.
things. Do you have thoughts on this? It's not that's not my area.
Because what we always like to say is everything, no matter what it is at some point going to be impacted. And the standards, like you just said, Peter, are a good comparative place, a good place to say, if I take this material and I test it to this standard under these conditions, and I get a set of data, and I take the other material this and test it under the same conditions, how do the results stack up? And I think an impact, to me, that's fine, but I want to know if my car bumper gets hit, I want to know how much, how much damages are going to be, but I also want to make sure whatever is hitting, the bumper gets hit, that it's been designed so that it does not let anything collapse into, let's say, the occupant's area.
Yeah.
So I think that, yeah, to me,
Yeah, I think there's an aspect as well that's standardization wise. I think on the really critical stuff, there are really
mhm,
well established industry standards
yes.
on collecting things like road load data
Mhm,
and collect and establishing real data.
mhm,
And I think it's something that I certainly don't have to handle because it's very much up at system level
mhm,
or even whole vehicle level.
mhm.
Um, so we're kind of servants to that business that
Yep.
then decides. But we work really closely when there's a materials testing standard. We're good. We're
Yep.
that's our remit, and we always make sure that we can hit that. So,
All right, we'll move on to looks like maybe the last question we'll address here. How can we capture more meaningful insights from dynamic testing rather than just pass-fail results?
well, in The simple end of that is exactly what Stephanie said about the same answer as instrumented impact. If you instrument, then you will collect a lot more data. You can get a lot more insight into things like energy absorption. If we turn it over to the fatigue side of things, um, well, there's an aspect of you can do really basic tests and say, does it survive 10,000 cycles or whatever? But most of the time, you're looking at building up a relationship. So you test a number of specimens. How do we get more meaningful data out of that? But again, it's the same idea of what some people refer to as data-rich testing. You've got a lot of data, you've got your position, you've got your force measurement, maybe you've got a strain measurement directly on the specimen. You can take certainly at up to moderate frequencies, we have the option for a video extensometer, which will provide that for plastics. With that, you can do calculations of what the elastic modulus for the material is. You can look at the energy absorption. So one of the nice things about plastics is that they are quite damping, certainly compared to metals. Aluminum and alloys are very, very stiff, very elastic. So there's some stuff you can do there with. You collect a lot of data. You can make calculations live while the test is running, and track how that behavior is changing during fatigue. I think those are the things that occur to me. Stephanie, do you have any other thoughts, sort of just following on from our earlier comments on energy and that sort of thing, or?
No, I think you've covered them, Peter, because you know,
Sure,
yeah.
sure.
All right. So with that, we're going to wrap things up, but I have a couple quick notes and reminders. So any questions? I do see a question that we'll have one of our presenters follow up with afterwards, and if any other questions come in, I'll be sure to get those over to our presenters, and they'll follow up by email. This was recorded, so the recording will be shared with everybody that's here today. It's coming up. So I know this is an automotive session, but if you happen to be in any of the other topic areas, consumer goods, medical devices, or our last session, I know these are later in the year, so you can reserve your spot and you'll definitely get reminders. That last session is going to be about automation and plastics testing. So I think all of these are going to be real interesting sessions. So I encourage you to check that out and get yourself registered. And then finally, when I close out the session, a brief survey is going to show up. We'd really appreciate your feedback. So with that, thank you to both of our presenters and thank all of you for joining us today. Appreciate your time. Take care, everybody.